Ladies and gentlemen, here we go. This is 10.1, day 2. 10.1, day 2. We're going to look at several ideas again that we looked at yesterday or Tuesday, and add some more to it as well. We're going to address the infamous 1 plus 2 plus 3 ... and look at some more of these power series and talking about converging. So, warm-up question. What do you think about this, converge or diverge? So, we gave those definitions on Tuesday, just kind of informally. So, that's what I'm looking for right now. What do you think? Does that converge or diverge? And we'll tackle that today.
It follows the negative extra. Oh yeah. We're gonna start doing this now. I do a lot of it. I know that you do. I'm definitely gonna do this. It follows except for the only thing is
All right, so what is your intuition kind of about this? By the way, do I call that a sequence or a series? A series. Converge or diverge? Votes for converge. So if you say it converges, then you're actually saying what? Yes, we're going to be able to say it equals to something. Votes for diverge? No votes for diverge. Some of you didn't vote. But if you were going to choose diverge, what are you saying about that sum? Goes on forever. Tell me more. So we're going to be growing in some sense. Getting further apart's an interesting comment here, because what do you notice about this specific series? We give a name to it. It is getting smaller, and it is something about this positive and negative. So here's the phrase we're going to use. We're going to call it an alternating. It's alternating. There's a negative 1 to a power that keeps happening here. And CJ, that's why I think when you're talking about like that between element, like that's really growing further apart or growing closer together. That's something here. So what made you say converge? Just because it gets smaller? Suhas?
Yeah, so as you go on, the value gets smaller and smaller. It's not going to affect like the overall.
Okay, that's an interesting comment there, where he said it doesn't affect the overall. What do you mean by that? That's actually going to be part of the lesson today.
Well, so I think about like the horizontal axis. So like
Okay.
we're going to be getting close to a number, and then the size change is going to affect the actual.
Yeah, so we're going to hold on to that thought. That is a really good idea. Like we're adding things on that somehow aren't impacting the stuff that came before it as much at some point. So obviously we're going to need some better words and definitions here as we go, but that's kind of a good starting point of converge or diverge. So as we're still thinking about this converge and diverge, I want to detour back slightly and talk about Tuesday. And you should have in your notes some power series that we made, right? Here was that first one. This is that geometric that geometric pattern, the geometric sum. We have an R value between -1 and 1, which I've called X here. And then we would say that that infinite thing converges. So I want to give an example of what I mean by that. Okay, so of how is it that I could have a power series converge, and I want to help you see it graphically. And this is going to relate back to these other comments. Suhas was talking graphically about a horizontal asymptote, so we'll see how this maybe comes back together here for us. So, yeah.
The coefficient is smaller than 1.
What do you mean?
The coefficient of each one.
So, maybe. It depends on several other things. We'll actually do some substitution here and play with that a little bit. Okay. So first thing is when I say this converges. So here's again that piece that we've got to kind of get our head around. That this function right here, I'm saying is equal to that infinite polynomial. I'm saying they're equal to each other. Now, if I do cut this off at like this x to the fourth, if I cut it off, then they're not equal any longer, right? They'd be approximate. But with the dot, 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 I'm saying that they're equal. And that, again, geometric sum, infinite sum, we kind of derived that formula the other day. So here's then what we're saying. If this is the interval of convergence using our language from Tuesday, if I pick an x value like a third, then, so that's what I've done down here in the bottom of the screen. I just substituted and wrote that in. That means that this infinite sum is equal to 3/2. And I think we looked at an example. I said an example like that at least briefly. But here's what I want you to see it. I want you to see it different. Okay? So here's what I've done. Hopefully this makes sense. I have the function here in red. One over 1 minus x. Okay? And we just said that that's the infinite geometric sum. And so here's what I have up here. I have actually terms that as I drag this value, I'll get more and more terms. Okay? So here a is 1, so look at these two terms right here. So x to the 0 plus x. So those are really the first two terms we would have. And again, when you look at this graph, you're not going to suggest that this graph is the green graph is a very good fit of the red. Okay? But look what happens. Let me try to zoom out here a bit. In fact, yes, let me maybe change my y-axis here slightly. Right click. Just wanting you to see this. Maybe I just should zoom back. You see that in here that the graphs look very close together? But then as I zoom out, I don't see that as much, right? As I scroll over here to the left, they actually start to separate. So for what x value do these functions agree? Just as they are right now. For what x values, if any, do these functions, red and green, give the same answer? what x values does the green function and red function give the same answer? Graphically, you probably should have a guess. And then you could check that. What is it? What? 0. If x is 0, what are they both equal to? 1. And so the graphs are on top of each other right here. But they're actually not on top of each other. Really, well, they're separating on either side. So here's what I want you to watch. Let me go back here. Look what happens as I add terms. So this is 1 plus x. The next term would be plus x squared, right? Plus x squared, plus x cubed, x to the 4th, 5th. I'm going to keep adding terms on. So again, it's geometric. I'm now out to x to the 64th power. My computer just stopped responding. It doesn't like it when the numbers get too big here. There it goes. So x to the 100th, it's adding those all up. So there's a polynomial of degree 100. How do you look at this and understand interval of convergence? Talk about that at your table. How do you see it graphically? It's staring at you, this interval of convergence.
I know, but if you look and see, like,
Yeah.
one is in no, it's not. It's not
How would we describe it? So this understanding of interval of convergence, how can we see it graphically? What would you say? Alicia, what would you say?
So, graphs of the functions only match within the interval of convergence?
Yes, the graphs of the functions are going to match in that interval of convergence. Now, they're really going to match then perfectly as what happens, though? Because are they perfect in the interval minus 1 to 1?
Power goes to infinity.
Yeah, so we still need that power to go to infinity, but here's something to think about. Could a polynomial, a single polynomial, ever deal with matching this entire curve if there's an asymptote here? Right? That doesn't make sense, really, right? How do I have a polynomial that is continuous, right? Polynomials are continuous, that somehow is going to match this thing perfectly when this thing jumps over some
Is it
asymptote?
alternating?
You all right? Okay. So this one wouldn't be alternating unless if x was a negative value, do you notice that this then would alternate? So alternating ones can look like that still, look like all positives if that's what you were thinking about. Okay? So what I want to do though, and something we haven't done, is take this thing and change this interval of convergence. Okay? We were really focused on Tuesday of this minus 1 to 1 and these intervals. So let's go back here. So this is the statement that we were just using on the other screen. 1 plus x plus ... 1 over 1 minus x. It's just geometric. It's just that formula again. And we know that's going to converge between minus 1 and 1 there. So what I want to do, though, is somehow use what I know and a substitution to now try to match that function. So I could go back into GeoGebra and I could change that other function to 1 over 5 plus x. And I want to know what I'm going to do to substitute here to do that. Okay? So look here, and decide. What would 1 over 5 plus x, what would that look like if you could write that up?
I don't know.
And then it would be like the y-intercept would be after that. And it would understand, I don't know if that changes the y. Doesn't the base keep?
So you're saying it's plus
No.
no.
Does it change every output?
So,
But like,
what
the same
substitutions that you make in that
when I get the thing off bar, it tells -1 is less.
so what would x be in that top equation? So look at start at 1 over 1 minus x. So what would you substitute x that would produce 1 over 5 plus x? That's the goal.
Well, actually,
It might help. It might help if you would think about, if you want to call this a different letter for a minute, like if you want to call this U, for example, or something, and then, so really I'm asking what's the relationship between x and u, if I'm looking here and looking here, such that I would get that. So if that's a helpful thought, use that, but there's definitely a substitution here that will make this, which means you should know what to write here.
Well, I guess how do you get 5? The first one is 5. And the rate's x. One's just a constant. Did you follow that, Alex? That's why I don't know.
You need us to explain it kind of slower.
I do too. Yeah.
She just attacked you.
I've never had to let him alive.
You have to suspend her. Give her a pink slip, Lucas.
So, is it
I also lost your top half of the ground. Or is it?
It's still going to be 1 because the second term so whatever your substitution is,
Something will get the multiplier by
Okay, back up here. What would x be that would produce 1 over 5 plus x if I look here? So what substitution are we really making, Colin?
-x minus 4.
So if x is replaced with -x minus 4, well, first, does that give us 1 over 5 plus x? Yes. Sure. So that then means you should know what you could write here. So 1 over 5 plus x is actually what? So it'd be 1. What would these other pieces look like? Write out a couple. Write out a couple of those. And answer this question. What is the interval of convergence. Okay, so the interval now of convergence, we've substituted, so it should have changed. Can you tell me what it is? And I'll try to show it to you graphically here.
Now I know how to call
Oh, wait,
this
either-
Dr. Thompson.
Because we have your symbol. The common. So you don't have the I should know the x plus y, the x plus.
Because things are gonna like, oh, here we go, we have to worry about these.
No, because -6 to -4. 4 is.
I know.
Yeah, I guess. So what, yeah, I have to just subtract 5, 4 from every single egg.
So 1 plus x minus 4 plus x minus 4 plus x minus 1.
Yeah, I subtract 5.
Okay, so writing a few out isn't that much of a challenge. It's probably answering the next question then. So the interval of convergence. Somebody want to propose one? Colin?
-5 is less than x is less than -3.
-5 is less than x is less than -3. Who's on board with his? So that is correct. Meredith, how do you get that?
You take the starting interval and then, or the, well, so it's -1 is less than x is less than 1, and then you, instead of x, you would do -x minus 4 and so that.
So you start with the statement that you know is true, and then say that last part again. Then you did what?
Replace the x with the -x minus 4.
And then what? And then solve. So you're just solving that inequality. How many of you did it that way? Okay. Did anybody think about a graphical transformation?
No, I swear I actually did, but then I just thought it'd be easier.
So this goes back to something you've learned since Algebra 2. Like if I say f of x is x squared, and then I say f of x minus 2, don't you know how that function has been transformed? Like we don't need to look at the graph, it's which way. This one is right too, right? Correct? So that means that if you understood what that first graph looks like, now there's an extra negative here, so we have to be careful. Which way, if you think of your interval, you know which way this graph has been transformed. The interval was, what? -1 to 1. You say it's now -5 to -3, so which way has it moved? Left 4. It has to be left 4 because there's actually an extra negative in there, right? Minus x minus 4. So you could factor that out. So take a look at this. This really then is a picture of what we're doing here with convergence. So here's the 1 over 5 plus x, red function. Asymptote at -5. Okay. Again, that kind of is pointing to the fact that it's going to be hard to have a continuous function continue to agree past the asymptote. How are you going to do that? So suggesting that Colin's right. And so as I add terms here, and because it keeps alternating even odd, even odd, even odd, even odd, right? And we can see we're matching the function from minus 5 to minus 3. So here's the picture I want you to keep in your head of interval of convergence is where that polynomial equals what that sum is. There's definitely numbers where it's not true, right? So when you're thinking of this as an equation, this 1 over 5 plus x, if x is 5, that would say 1/10. Well, we would never expect to put 5 into the black function and get 1/10. Right? Because graphically we can see the functions don't match at the x value of 5. So whenever I would apply a formula outside of this interval of convergence, crazy things happen, right? I could just say, oh, the answer is 1/10, when it obviously can't be, because we're beyond where the functions agree, going back to what Alicia said. Okay. So, any questions on taking a power series and shifting it? Because that's really all we've done here. Shifted it left. Shifted. So, next thing I want to talk about, still on this theme of convergence, is addressing that kind of intuition you had that that first thing was convergent, which it was. So let's go. Oh, real quick, just a language thing. On that last question, when we gave the interval of convergence from minus 5 to minus 3, if I would ask you what the radius of convergence is, what would you say? 1. It's still 1, right? Because it's half the distance. So radius is just asking what's half that distance again. So that's why it's less helpful. You know, the interval actually tells you where. The radius just says how big is it. So, all right. Here's the following sequence. So you can title, if you want to put a line and label this sub portion of your notes partial sums. Partial sums. Partial sums is a way to kind of reason and think about whether something, as I'm adding them up, whether it's going to converge or not. Okay. So here's a sequence. I'm calling it a sequence because it's just a list, right? I'm not adding them together. And so I want to start asking this question like, does it converge? Okay. And so if I'm thinking about changing this to a series, like this is actually a pattern. What is this? If I had to ask you what kind of sequence that is, what would you say? You should say geometric. And what does that tell you about the sum of that sequence? Is it going to converge or not? Yes or no?
Yes.
Jade, yes, because? It's dangerous to agree.
Because it's just like the first one.
Why? You could answer this by just, it keeps getting smaller, which means R is, well, what is R here if we're thinking it's less than 1, right? So that's why the terms are getting smaller. And since it's geometric, that sum of those has to then converge. In fact, do you know what that answer is going to be of the sum of these? It's 1. Okay. So this is actually going to equal 1. You could do that formula that we actually just did to get this answer. But what I actually want to do is explore something called partial sums. And when I'm thinking about partial sums, I'm actually just looking at this as this sequence. Okay? And so the partial sums say this. So the first partial sum is just adding together the first number in your sequence. So S1 here is just 1/2. So that's the first partial sum. Okay, try to keep this all on the screen. The second partial sum is actually adding up the first two numbers. So in this case, it's 1/2 plus 1/4. And a half plus quarter is 3/4, so I just went ahead and wrote down what that answer is. So the third partial sum, so now we've added the first two together to get the second. So now add the first three together. A half plus quarter plus an eighth is 7/8. You can do that arithmetic. I hope that's not what the point is. So what would S sub 4, the fourth partial sum here, be? Yeah, do you see that? Do you see that there's actually this pattern that's forming here? That, what's the next one going to be? Yeah, 31 over 32. The next one's going to be 63 over 64. So here's what I want to first ask. Why can these partial sums, so as S increase, so S sub 6, S sub 7, S sub 8, S sub 1,000, S sub 10 billion, what about this sum, could you argue, is why it will never be bigger than 1? Like, as you're observing this, we're going to be more specific here in a minute, but I think you could make an argument right now that no matter the number I choose, if I want to add up the first 10 billion numbers in this list, so S sub 10 billion, based upon what's happening, that number cannot be bigger than 1. Talk about that at your table. What's the logic that might help you?
If we keep doing it over and over again, the numbers keep getting smaller and smaller and smaller, and so we're really adding
No matter what, because you always multiply both by 2, but the numerator's always 1 less than the denominator, and so we multiply it by 2, we cap 2, and you add 1. So
All right, so back up here. Amit, you noticed something. So as you're moving from 3/4 to 7/8, talk to me about the amount that I'm actually adding. A half of the last value I added. You could also say it as, so this half of this quarter is the amount that gets added back on. But aren't we short by a quarter? Which means this one must be short by an eighth. For the same reasoning, this one's short by a 16th, and so on and so on and so on. That's what some of you were probably doing when you just started reading them off to me. You realized that, oh, the next one is, well, it's doubled 64, so 1 less, 63. The next one is 127 out of 128, right? It's got to be that same pattern because it's always half of that previous amount that we added. Well, that is kind of compelling to say that this sum really is the number 1 then. Why is that agreeable to you? Like, Alex, you shook your head yes pretty quick, that, yeah, that makes sense. What are you thinking?
Well, because that sequence is going to infinity, so like the partial sum is going to be approaching 1. So at some point we can say that it's like close enough to 1 that it's
But if it's a limit, I actually never stop, right? So then it doesn't even matter if it's close enough that I can't tell the difference. I'm always progressively getting closer, right? Always closing that distance. So let me say it this way. Is there any other number that would make sense to call this sum other than 1? Well, you could call it 0.9 repeating.
Well, you decided that's equal to 1.
So that's just a redundant answer. That's the same answer. I would give full credit for such answer. But here's why you can't say this sum is 0.99. Not the repeating, but just 0.99. You would not want to say that this sum is 0.99. Why?
You could put that it's just going to be, you're going to add something else later than the drill one.
So eventually, what's going to happen if I add enough terms? It's really what she's saying, that I'm going to be within that 0.01, right? I'm going to be closer than I just said. So again, is there any other number that makes sense to call the sum other than 1? Because any number less than 1, I would say, what would happen? Eventually, I'd get a number between that number and 1. I would always close the gap, but I'm never going to pass it. So that's why this answer is 1. So here's the statement. So jot this down. I'll tell you what I'm saying by it. So I'm saying the limit as n approaches infinity of s sub n. Okay? The limit as n approaches infinity of s sub n is equal to that summation. And what you just talked about is really this statement. So it's not this fantastic statement. It's a pretty, okay, that makes sense. All this is saying is that if I keep taking partial sums, and n keeps getting bigger, n goes to 1, 2, 3, 10 million, 100 billion, and I add those all up, whatever the limit is, as n goes to infinity, going back to Alex's comment, of whatever this partial sum is, as I keep adding more and more terms, that answer has to be the same as the original thing that I was trying to think about adding up. That's all this is saying. So this initial summation here is saying 1, I'm sorry, half. We started at half for this one. So a half plus a quarter plus an eighth plus dot, dot, dot. So we're looking at, on the right-hand side, what that is. And the left-hand side says, well, if I take these partial sums and I let n keep getting bigger, whatever that approaches, those things have to agree.
So half would be A1, and then we're just saying that it would approach A0.
So this is saying if I put in 1 to this, I get A1. So the first number I'm adding is a half. The second number I'm adding is a quarter. The third number is an eighth. This side is saying the sum of the first n things added together, as n gets big, whatever that comes to must be the sum. Okay? Still with me? Now, that, I hope, makes sense, because if I just keep adding and adding and adding and adding, shouldn't I be getting to the answer of what the sum is? Okay, so. But here is where we're going to start to debunk that 1 plus 2 plus 3, etc. is negative 1/12. Okay. Do you know, like, that video's been viewed by like 6 million people who've been lied to about
Can you
some
please make a
thing?
reverse video?
What's that?
Can you like make a video on why that's fake?
Maybe you should.
Yeah. I will totally hype it up with this lecture right now.
Yes, so you
So,
Right now, can we just take that and put that on?
we'll see. We'll see. We'll see if this works to help you, still, if you want to argue with me or not. So here's what I'm going to say. If I can get an answer for this, if I can get an answer for this limit on this left-hand side, and I can call it something like L, then this summation must also be L. Now, I haven't actually proven a minute ago that this answer is 1. Other than using the definition of a limit, that there's a formal definition of a limit that we actually haven't explored. And it's this epsilon delta proof that we could go through, but effectively it's this. You can always get closer to the target than any goal that you would set. So like that's why I was asking you that 0.99. I can move past that closer to 1. 0.9999. I can move past that closer than 1. So I can always move closer to it, so that's why 1 is the answer to this. But I'm going to do it slightly different here in a minute. But here's some things then to think about. So if this L isn't possible, or if this L goes to infinity, then we have a divergent thing here. So if this L isn't possible, or goes to positive or negative infinity, that thing diverges. Because they have to agree. Okay? If they didn't agree, then none of the summation would really make any sense. So that's all I'm saying here. So there's really this partial sum idea that Those two must agree. So if that one is L, where L can be found is not infinite, then the summation that I was after is actually have to be L. Okay? You can jot that down if you want, but that's really just in words, in symbols, what we've been saying in words. All right, you ready? It's actually pretty simple to show. Because, let's go here. How many of you, by the way, have seen that video on YouTube because Shoria wanted you to watch it, that 1 plus 2 plus 3 plus 4, etc., ... is negative 1/12? Who's watched it?
Oh, I did try to force it, but I resisted.
Okay, good job, Nick. Good job. So how many of you have seen it? About 5 of you? Okay.
Well, I mean, they count for like 500,000 of those 6 million views.
So there's these, they're not dumb people, right? There are 2 physicists that work at a university, I think. I don't know. That is, don't go there.
Yeah, I know. That's
Yes. And they do some manipulation that most of it isn't valid because they're violating this idea of convergent to start with, but they end up saying that something like this. Now, it seems pretty convincing in what they do. So, like I said, 6 million people probably walk around going, math doesn't make any sense, we should throw it all away. If you put this down on any, hopefully, at any calculus test at a university, any math professor worth anything is going to call that nonsense. It is. It's like the 0.9 repeating challenge. So here we go. Here's the summation. So here's what we're going to try to do. I want to find the partial sums. And whatever the partial sums do in the limit as n goes to infinity, this thing does. That's the logic, right? That's what we just accepted a second ago. So whatever the limit of the partial sums is going to do, this summation does. So let's try to write this out. So if this is my thing that we're adding, right? So remember our summation notation, plug in 1 plus plug in 2, et cetera, et cetera, et cetera. Do that forever. So S1, so the first partial sum, second partial sum, go ahead and start writing. You just need the answer, okay? So again, I'm not saying what the fourth number is. We all know that's 4, but I'm saying the sum of the first 4 numbers. Or S of 3, the sum of the first 3. So here's the thing then we have to do. Now, I think even looking at this, you could say that you're done. That you're done. But we're going to do it one better. Because what should be happening here if I'm going to be able to say that there's an answer? Alicia?
They should be going towards a number.
Yes, they should be tending towards something, right? This seems to say that as the n value increases, does there seem to be any limit on what the sum is going to be? It just seems like it keeps growing. But some may argue then, well, wait a minute, you're just you're not addressing the issue. So let's be more specific. Can we write a formula for what S sub n is? We can. Can you? Or I can. Can you? There's a pattern here. So think about, you did some of this in pre-calc. Like you would think about this kind of like a formula, trying to write a function. right? I need a function such that when n is 1, the answer is 1. When n is 2, the answer is 3. When n is 3, the answer is 6. So, and I'm wanting to write that as s sub n. I'll give you a hint. It's a product that's being divided. So, can you do it? I'll give you a minute.
So between 1 and 2, 2, 3, and 6 and 6 and 10 is 4, 10, 15. I'm gonna write that. And welcome to my struggle. I see the pattern, don't know how to make it into an equation.
Recursive is like the previous thing times the next one. This won't be recursive. Yeah, don't do it recursively because that doesn't help you, because then you have to know all of them to get S sub 30. So I want a formula that will work for any n directly without knowing everything in between. So I hope you see the pattern, but that's not enough. This is really this part of this problem is the hardest element to come up with a function. If you come up with a function, we'll be able to make our argument as to what the sum here really is.
I mean, it is infinity. If you think about the sum of all of them, you can keep growing forever and ever. Oh, wait. N times 1 plus 2. If 1 has 1 minus n over 1 minus
There's a hint. There's a hint.
I'm trying to see 2 times 3 is 6 divided by. It's not. Oh, yeah, I know that. 10 plus 1, not n minus 1.
Yeah, but 4 times 5 equals
20 divided by 2, 10.
Oh, I was thinking like.
Yeah, you had it, you were this close, girl. Like,
Who sees the pattern? So look right here. Here's a hint. 2 and 3, 6. 3 and 4. See it. N times n plus 1 over 2. Okay, so here's what we now have. We have a formula for the sum, any partial sum, right? This is any partial sum. If you want to know the sum of the first 1,000, 10,000, 100 million, just put that n value in there and it gives it to you. So here's then what we need to do. If this is the partial sum and it has to agree with this summation, then I really just need to think about the limit as n goes to infinity for this formula. Well, what is that? Has to be infinity. So the partial sums go to infinity, and there's really not an argument because I have a closed form to represent every partial sum, which means that original summation must also go to infinity. This divergence. This part is the hardest part, coming up with the function. At this point, I'm not really going to ask you to do that much. I might give you some, and we're going to look at a couple examples here, because there's another element that's in that video, another series that they use that's also wrong. conclusion they're drawing. So if you take a bunch of false things and put it together, who knows what comes out, and that's all they've done.
What's the argument made in the video that somehow they got one wrong?
I'll show you on the next one. Show. Okay.
Yeah, even stranger.
Yes, negative.
Add an infinite series of positive numbers and get negative.
So this is actually connected to part that it's a series like this that they're going to use to come up with an answer and combine it together. So when you think about this one, and I just try to write out, what is this telling me I'm adding? Like, what is this wanting me to add? That's summation notation. What is it really saying? Negative 1 plus minus 1 plus 1 minus 1 plus 1 dot dot dot. Right? That just goes on forever and ever and ever. Okay? So, in that same video, they're using a thing that is between two, and they say the limit is just the average of the two numbers. So here that they would say this answer is 0, which you should probably kind of bristle at. Plus 1, minus 1, plus 1, minus 1, plus 1, minus 1, plus 1, minus 1, but yet we're going to call the limit a number that we're never at? Only when I'm adding two together, but I keep moving on? That seems strange. So let's look at the partial sums, because the partial sums will answer this. Okay? So S1, S2, S3, S4. Just start writing out what these are. First partial sum, what is it? First number. That's easy, minus 1. Next partial sum. Next one. Next one. Right? Plus 1. We just keep subtracting 1, adding 1, subtracting 1, adding 1. Okay. So, if I would ask this, pen, come on, pen. Yeah, I don't like this one. Sorry, my pen stopped working. So when you look at this partial sum list, if I would say the limit as n goes to infinity of s sub n, what would you say? So it's minus 1, then it's 0, then it's minus 1, and then it's 0, and then it's minus 1, and then it's 0. There is no limit. There's no limit. There's no limit. We don't approach anything. We just keep bouncing around. So this also diverges. So again, mistake number 2 they make in that video is they say that something like this, they just pick an average, which doesn't make any sense. No. So,
Yeah, according to that, that means sine and cosine. Their limit is 0.
what do you mean?
According to them. According to that, because it also is negative 1 and 1. So the average is 0.
So then they would say 0, yes. So the limit as for a sine curve of going to infinity using the same logic, they would say 0, right.
Yeah, that is.
How about this one? Okay. This one's different. This one's different. Oh, I'm sorry. I this should be a 1 and minus 1. I changed it, and I forgot to change that second one. That should be a 1 and then n minus 1. Now, if I just ask you to guess whether you think this thing converges or diverges and have some reason. So I'm adding things up, summation, right? I'm adding a bunch of things up. Converge, diverge. Votes for converge? Okay. Why? David.
it's something of like super common as your n gets bigger, you can make subtraction one, so you get like 3 can be something massive and then 1 massive.
Yeah, so thinking about that exponential growth in the denominator, how big it gets, he was saying massive, but I'm dividing by it. So this gets small actually very quickly, and that goes back to something Suhas mentioned very first moment today. How quickly it goes to something, approaching that asymptote. He was thinking about it graphically. So this actually is going to converge. Now, again, the part that is difficult to come up with, if I start writing these partial sums, so that's what I'm saying here. So look how I changed my notation slightly. So S sub n, so that's the partial sum. So I'm saying I equals 1, 2, so if n is 1, then this upper limit is 1. So that's the first partial sum. You could plug in 1 to that and get an answer. What is it?
1.
1. So the first partial sum is 1. Put in 1 and 2, so you get 1 plus a third, and then so on. 1 plus a third plus a ninth, and so on. It's actually this. This is the formula for S sub n. So jot that down. I know I'm running out of time here. So what this will give us, so S sub 1 you said was 1, just writing what you said, maybe. S sub 2 is 1 plus a third. S sub 3, 1 plus a third plus a ninth, right? And I'm claiming that this formula will match these final answers. And again, that part I'm not going to have you try to make. Okay, that's probably creative, 1, and 2, it can be, we might look at some more of that later, like how those could come about. But you could test that one. Now, your intuition was this converges, and that's not wrong. What does it actually converge to? So this summation, you should be able to tell me the number. If it converges, you told me at the beginning of class, you'll be able to say a number. This one converges to a number. What is it? So 0, 3 halves. 3 halves. It is 3 halves. Talk your table. Why?
The limit.
Why is it 3 halves?
If you said the limit, try to find the limit of that function. So between 3 times 1 times it. The one that you didn't get in, and be like
Cooper, that's fine. That's fine.
I volunteer at 4, bro.
So, why 3 halves? Can you make an argument? Susanna, can you make an argument?
So 1 minus 1 over that part is basically
Going to become what? It is going to become 1 as what is happening. Yeah, so as n goes to infinity, this is really, if you think about just an exponential graph, how this graph would be behaving, right? There's a horizontal asymptote there. This piece goes to 0, so 3 halves times 1, answer is 3 halves. Good job. So if you could come up with the function, then it's not so bad. How about this? Last thing, I know I'm out of time, I'll pay you back. Somebody can keep a record of some of the time that we go over and let me know when it adds up, and I'll pay you back. Okay, Colin's got it. Once, I think.
What is that? Sigma? Is that a Christmas tree? Wait, that's a little Sigma?
That's a great
It looks like a really bad I'm guessing it's gonna be.
This is one of the classic, most important ones for you to know. It's so special that we give it a name. It's called the harmonic series.
Oh, this is what you were talking about.
I mentioned it on Tuesday. And this again connects to this idea that, yes, it has to get small, but it also has to get small fast enough. And that's why I think, Suhas, the way that you said that was very good at the beginning, whether you meant it that way or not. But of course you did, yes. So, do you remember what you were talking about, the relative size? Do you remember what you said? He said something like this. So, Suhas, if this isn't quite what you said, feel free to adjust what I remember him saying is, when we're adding something on, it was the relative importance to the pieces that were already there. That the amount that we're adding on was small compared to what we've already added up, so therefore we came to a sum. Does that sound? I think you said it slightly different than that. But that's the idea, that we got to an answer because the amount that I add on was kind of not very significant compared to the amount that I've already added. Okay? Now, when you look at this one, it's tempting to say this converges. Because I would say 1 plus a half plus a third plus a quarter plus a fifth plus ... People will say it converges. Why do you think people would say it converges? Gets smaller, okay? But unfortunately, everything that gets smaller doesn't necessarily come to a sum. So take your calculator. This is pretty easy to see in your calculator. Okay, so here's what I want to make a guess of. Go ahead, Alicia. Don't do anything yet. You don't know what you need to do yet.
I don't know, I'm making a guess that the two terms that follow the previous have to be less than 50. Because that's how it was with the function that is convergent for this. If you took 3/4 and 1/2 and added them together, it would be 7/12, which is bigger than 1/2.
Yeah, there's a pattern here that as I keep adding this next term on and compare it to what was already there, so you'll start to see this even just in your calculator. So what if I said this? So this is 1.5 plus a third plus a quarter plus a fifth. What if I would say that this answer is less than 3? How would you prove me wrong? If I make that claim, I claim that the sum of those infinite number of numbers from 1 to whatever, right, just keep going, that answer is always less than 3. How would you prove me wrong? Lauren, what?
Huh?
Did you say it?
She didn't say it.
Livia, you said it? What?
How you just keep adding more.
And what would you look for?
A number higher than 3.
Yes. So does that happen? So take your calculator. So do 1 plus. So do this smartly. So do 1 plus a half, hit enter, and then you could just say plus a third, plus a quarter. Keep doing that. Just hit enter, plus a quarter, plus enter, plus a fifth, plus so on. Or you could, Olivia says it already happens at 11. N is equal to 11. Do you see how this is different than our conversation at the start of class when we said the answer was 1 because I kept adding, but I'm never going to pass 1? So, okay, if we can get past 3, can we get past 4?
Yeah.
Or 5? Or 6? Or 7? And in fact, that actually means this answer is infinite. Now, we'll be able to prove that a little bit more. Like, you could look at these partial sums, and you'll realize you have an issue, but there's also a graphical connection here. The function is 1 over x. If I'd ask you to integrate 1 over x, there's a connection back to what function? What is the antiderivative of 1 over x? Natural log of x. How big can the natural log of x get? Is there a limit to the y value for the natural log function? No. So if I keep moving further over on the right, wouldn't I be plugging in a bigger and bigger value for the upper limit? There is no biggest value, which means that area is infinite. Okay? We'll prove that a little bit more later, but that's a preview for it. I need to give you some questions from the book, which I haven't written out yet. So I will get those on the calendar here in a few minutes, and you can check those. Okay? Colin, you got the time?
Yeah, 13.
See ya.
Plus the 5 minutes for the last one.
So what is it, 15? Are we going to count early morning class too? Yeah, I can do that. No. At the end of the semester, I better get paid that much money for having to deal with all this. Okay, bye guys.